Oh, this is exciting for anybody who's looking in. Did I schedule a really cool mission on? Oh, I did. Look at this, John. I thought I'd give us a treat.
Ooh, look at that.
So I thought,
Wow.
before we look at the small white dot and start the star party, I thought, I can't resist. Orion's visible. There's the live view of Orion. We got a couple of quests, haven't we, John, to have Orion? Oh, no, it's
We
finished.
do. Not
I'm
only
glad
we
I
have
remembered to get to that just at the last minute. Just managed to capture us now. Sorry, John, I interrupted. What are the quests that are related to the Orion Nebula?
we have a quest that's specifically dedicated to the Orion Nebula called the Hunter, which is a fantastic quest. Goes through the historical connections with the Orion Nebula, goes into how what is observed, what it is you're looking at. If you're interested in knowing about nebulae in general, there's also Nifty Nebulae, which teaches students about those kinds of nebula. You can capture the Orion Nebula for that quest as well.
And that's one of the quests we recommend people start with, isn't it?
That's right. Yes.
Yeah. Oh, I've just seen that we've got quite a few participants rocking up in Zoom. We've got quite a few lined up to be watching on YouTube. John and I are just having a bit of a chin wag. We will go live probably at the top of the hour. Bewitching hour here, John, in the UK, and in fact at the Canary Islands Observatory. What time is it over there on the West Coast?
It's almost 5 p.m.
5 p.m. So you're at the end of your working day.
That's right. End of the workday, time for a star party.
Exactly. Why not? And my work day finished, well, it kind of drizzled out today. It didn't really finish, and here we are. But can we really call this work? I don't think we can we?
Yeah, it's just
I do feel
time
lucky.
to come together.
I do feel lucky to this. Look, this is Slooh homepage. If anybody is joined us a little bit earlier, we are just having a bit of a natter, John and I, before we launch ourselves into Near-Earth Asteroid 2023 DZ2. So how would you say that, then, John?
I would say that DZ2.
DZ2. I would my English tongue would trip over that every single time I tried to say that. So DZ2. It sounds like a rapper.
It does. DZ2.
So, but anyway, we're gonna this is this new website, and we've got some great graphics. This is a photo that we took a few years ago, actually, when we did a special project with Vodafone over there. And this is the Canary 1.5 meter telescope. We are going to be using that tonight. This is the Milky Way stretching up. And I hadn't actually seen this new tagline that we got, John. See it live, see it together. There cannot be a more appropriate tagline, given that we're doing our first public star party for a long, long time. Any viewers, do excuse me if I seem to be looking over the camera, because I'm looking at another screen and stuff like that. But we were just having a quick look. Go on, John.
Viewers, I have to admit too, I have a second screen as well up here where I have all of the telescopes up and everything. So if you see me looking around, that's why.
I want to refresh his page, because if anybody joined a bit late, there it is. There it is. I just wanted to show people. I was very cheeky because we're going to be looking at a very small white dot this evening. We're going to be starting probably in about a minute's time. I couldn't resist. I set up a mission using one of the telescopes. This is the Chile 2 telescope. I'll tell you all about those in a sec. Of the Orion Nebula, and this is exactly what it looked like a minute ago. If you missed it in the live view, I love the Orion Nebula. So, anyway, we are nearing time. We'll have one last sip of water. I'm looking forward to this. This is such a terrific little asteroid. Well, little. We'll talk about the size of them in a bit. But right, Serenity. So we've got a whole bunch of people in Zoom webinar. Welcome, everybody. Actually, look, it's time. It is bewitching hour here in the UK, which is the same time zone as our Canary Islands Observatory, which is what you're looking at there. Our Canary 1.5 meter telescope. Got 8 telescopes all in all. Got a whole bunch in the Canary Islands at the Institute of Astrophysics of the Canary Islands, and we've got them in Chile as well. And we've got live views of this lovely asteroid tonight, this near-Earth asteroid. So anyway, if you are totally new to Slooh, what are we? Well, we're kind of an education platform, but it's not just for students. Anybody can join as well. Students, parents, anybody, space enthusiasts, what we call them. And we're going to show you some live views. And actually, this is the system, and all the telescopes that we're going to be looking at tonight, John, are available for all members to use. And actually, John, since we've been nattering anyway, and since I've mentioned you there, I was going to introduce you in a bit, but I would like to welcome my co-host, Dr. John Bovair, who is Slooh's Director of Curriculum. Have a formal hello, John.
Oh, thank you so much for that formal hello, Paul. I'm so happy to be here. And happy to look at this dizzy comet as it rolled by.
Exactly. So, Dizzy, what is it that we are actually going to be watching tonight? Well, it is a near-Earth asteroid. John is going to tell us all about that this evening. This peculiar name, they've got some really weird names, but it's NEA 2023 DZ2. I'm in the UK, so I said DZ. We've just been discussing this before the Star Party started. John says, what is it you say, John?
DZ2.
DZ2, DZ2. So anyway, that's what we're going to be watching, but it's been nicknamed Dizzy, partly because of its DZ2 designation, its formal scientific designation, but also because a lot of asteroids and indeed comets spin really quite fast. So this little thing that is whizzing between the moon and Earth, it's already kind of coming through. It makes its closest approach to Earth on Saturday evening, but it's far better place for most people, including both of our observatories, to view tonight. So we thought we'd get an early look, and frankly, we're not going to be disappointed. So don't forget, if you're new to Slooh, if you're not a member of Slooh yet, you can join. You get to control all of the telescopes that you're going to see tonight. You're going to be able to join a worldwide community of fellow space enthusiasts, students, teachers, educators, professors. We've got people all around the world using Slooh's educational astronomy platform. And John, I'll maybe quiz you a little bit later on exactly how students are using it. But I think, don't you think, John, we should take a quick look at the dashboard. So this is just a homepage. Absolutely. If you want to check out www.slooh.com, you can check out exactly who we are and what we do over here. But once you're logged in, when you join up, this is where you land. And there's a whole stack of stuff on here. We're not going to go too heavily into this because we're going to go very quickly over to the live telescope views, because I know that's what you're all here for. But anyway, we can take a quick scroll down here and we can see all the missions I've scheduled. And most people have not got this number of missions scheduled. It took me about 3 hours today, John. I think we've got, I don't know, in excess of 60 missions or something set up. So a mission at Slooh is a 5 or 10 minute period of time where one member has scheduled the telescopes, pointing one of the telescopes to a specific object. But we kind of call Slooh a celestial jukebox because all members get to watch all of the live telescope streams. So I think with that, John, I think we should go and take a look. Which telescope shall we start with? Shall we start with the biggest?
Let's start with the biggest.
Start with the biggest. This is at our Canary Islands observatory. This is our Canary 1.5 meter telescope. Now, telescopes, that size that you hear is about their primary optics. And in this particular case, it's a mirror and it is 0.5 meter in diameter. That's 20 inches in old money. Or for you, John, I thought I'd just do that quick translation for you. I think we're going to cover kind of meters and feet and yeah, all sorts of things, kilometers, miles per hour. But here we go. Here is our first view from the Canary 1 telescope. So this is a live view coming in from that telescope. We've got a little bit of fuzz over here, John. Any particular reasons why we might have, a little bit of noise in the image? What are the conditions like? We can take a look, can't we, down here?
Yeah.
All sky. Oh, look at this. That's a pretty yellow sky. That's a pretty murky looking sky tonight. So So this is our
So-
all sky camera. So 180 degree view above the domes, and here you can see that Canary 1 telescope here pointing up, so we can even see where it is, where the telescope's pointing to. But John, here we are with this live image stream. So where's Dizzy? What's that book? Is it Waldo?
That's right. Yeah. Where's Waldo? Where's Dizzy?
What are all the white spots, first of all, that we're seeing in the live image stream?
Now, these white spots that you see here, these are all stars that are in our galaxy, the Milky Way galaxy. And, it may seem like these stars are pretty close, but all of these stars are really far away. And so we're looking for Dizzy, which is really close to us. So what we're looking for is something kind of nearby.
So this thing is moving at, what is it? Is it 17,000 miles per hour? That's its relative velocity, I believe. Which actually isn't that fast for a lot of asteroids. So
That's true.
I'm guessing that most viewers are seeing what we're seeing. All right. So don't forget, if you're in, by the way, Slooh members, be capturing and snapping images from the live feeds tonight, because next week I'm going to show you how to take those images and turn them into a time-lapse animation, which will be really cool. I'm just going to snap an image, and this is as easy as it gets. So don't forget, all members can watch all of the telescope streams. So here are all the telescopes up the top. We can watch them live, and we can snap our own image. So I've just snapped an image from this particular telescope. John, here it is. What's this little squiggly line down here?
That's right. That's it right there. That's the asteroid. So our telescopes, they take 50-second exposures. So for 50 seconds, the Canary 1 telescope is just collecting light. And as Paul just mentioned, Dizzy is really cruising through the inner solar system at 17,000 miles per hour. So in those 50 seconds, Dizzy went from one end of that streak to the other end of that streak.
And its apparent motion over time kind of changes. We might talk about that a little bit later. But last night I did some test missions for this, and actually Dizzy was just a single spot because it was so much further away. So the line just wasn't stretched out, but now it's getting closer and closer and closer. And tomorrow night, I suspect that over a 50-second exposure, that's actually going to be probably 3 times as long as it's appearing now. But let's take a look. Oh, look. So this one, John. So this is an interesting one. So now we've got 2 streaks here. Well,
what's happening here?
Well, it's how we build up. So, the sky's pretty faint. This little asteroid is pretty faint. So what we have to do with astronomical imaging, so the reason why we want a big telescope is because it captures loads of light, captures loads of photons, but we also have these ultra sensitive CCD cameras, which are cooled down to minus 40 degrees C. But we have to take a long exposure. But to build up even more and more detail, especially when it comes to galaxies and nebulae and star clusters and stuff like that, we take a series of images and we combine them to what's called increase the signal to noise ratio. It basically means we get rid of more noise and we see far more detail in the celestial objects that we're capturing. So what we're seeing here is a combination of 2 of those 50-second exposures that you talked about. So we're seeing 2 streaks, and we're also seeing a little gap in the middle. That's the gap between one exposure ending and the next exposure starting. But what we've got here, so I want to explain to members how we've set these missions up tonight, because we've set up missions on the Canary 1 telescope, the Canary 2 telescope. The Canary 2 telescope is a 17-inch telescope. It's one of my favorites.
Awesome.
Then we've got the Canary 3 Deep Sky telescope, and the Canary 3 Deep Sky telescope has a huge field of view. What's a field of view, John?
Big. I don't know off the top of my head, but it's
no. I mean, what is a field of view?
What is a field of view?
Yeah.
Oh, the field of view.
I wouldn't put you on the spot like that.
The field of view is the portal of the night sky that we're able to see with the telescopes. So you could also think of it as when you open up your phone and open up the camera, it's what your camera sees. And so depending on what telescope you're using at Slooh, the size of that field of view is a bit different.
Yeah. So the size of the Canary 1 telescope is slightly smaller than the Canary 2 telescope, which we'll hop over to in a minute. But what I wanted to explain to members is the way I've set these missions up tonight. Canary 1 is going to be tracking the asteroid. So what we're going to see is all the stars between each 5-minute, 10-minute mission. The stars will kind of move off up to the top right, and the asteroid will stay roughly in the same position. However, the other telescopes I've done slightly different. So let's hop over to Canary 2. So here's the Canary 2 telescope. And can you spot Dizzy, John?
I totally can. If I use the coordinates that are on the side, which are measuring out the field of view, it looks like, yeah, 10 and 5.
10
Wow.
and 5. Yeah, there it is. So what I've done with this one, and this is going to make a great animation for everybody. I'm really quite surprised actually at how bright the asteroid is showing up tonight. And we are going to talk, don't worry, we are going to talk about the actual asteroid in a sec, what near-Earth asteroids are. We're going to talk about its brightness actually, because it's very rare that an asteroid comes this close to Earth in a way that we can actually start capturing radar images of it where we truly know its size. But actually, so far, the size assumptions on this are based on a whole stack of assumptions, which John and I are going to talk about in a sec. But anyway, this particular telescope is set up. Look at that. And that's
that
a
is
classic
so
example
cool.
of it, the way that kind of transitioned into the next image. This is going to show a fixed field of view. So those stars over the hour are not going to change position. We're going to see the asteroid moving across at 12:30. That asteroid, that little streak, is going to be roughly in the center, and then it's going to go off at the top of the hour in 45 minutes time. I then switch, and we are going to then track the asteroid because it's going to go out of this particular field of view. I'm going to be really intrigued about this next telescope, John. So this is going now to the Canary 3 telescope. This is that telescope which has a huge field of view. Imagine the screen that I'm on at the moment. All right, the two telescopes that we've just seen have a field of view like this, would just capture my head. But
Wow.
the Canary 3 is way out to the edges of my cam. So let's take a look at how far this is. And we'll see far more stars in this particular view. Here we go. And here it is, John. We can see it. I'm so glad. I didn't know that we were going to see it in this particular telescope view. I'm just going to snap another shot of this because the telescope portal on this telescope, as you can see, is square, but the actual images this one captures are rectangular. And here we go. And hopefully members have been capturing this from the get-go, from the start of the star party, because it started up here, top left, and because it's got such a large field of view, we're going to capture this all the way through till actually about an hour's time. So it's, once again, this is going to be, actually, let's say that capture images of this, because this is the telescope that we will use to experiment, and I'll show you how to create some time lapses of this little asteroid shifting across the sky. I've got one more telescope to show you, so don't forget, images not great tonight because we got some haze, some very thick haze and dust there by the looks of it because it's yellow. Canary Islands, if you don't know, 300 miles or a few hundred miles off the west coast of Africa, which is basically the Sahara Desert. And what we can get when the wind blows in the wrong direction is something called La Calima, which is basically a dust storm that comes over. This is not too bad. It's not bad enough to keep the observatory close night. But let's go to the southern hemisphere, because Slooh has 2 observatories at the moment, one in the Canary Islands that covers the entire northern hemisphere of the sky, one in the southern hemisphere. I'm sorry, John, we are slightly going off our talking points, but we are going to get there in the end.
Oh, this is important.
We've just got so many new people joining us tonight. I want everybody, I want to do a little bit more of an explanation of Slooh itself, but we've got the Chile Observatory as well, which is at the Catholic University in Santiago in the Andes. And that gives us full coverage of the southern hemisphere sky. But this is the first time I think we've said this publicly, John. I am currently working, in fact, we've signed a deal to open a new observatory this summer. It's actually going to be winter down there in Australia. This is going to give us 24-hour coverage. So students using Slooh, normal members using Slooh, you are going to be able to rock up to the website, and weather permitting, there's always going to be a telescope live. So that's a pretty cool thing, isn't it, John?
That's going to be so awesome.
So anyway, that's Canary 3. Let's hop over and have a look at Chile 2.
Oh.
And here it is. So once again, this one I've done on a fixed field of view. There it is. It's interesting, not quite as bright. But actually, John, before we talk about the Near-Earth Asteroid, I just want to talk about one thing. Actually, just if you have joined late, I know we're looking at a lot of small white dots tonight and a small white line, which is the asteroid. I hope you didn't think you're going to see it like you see it in some of the media pictures. But most of the time, this is what members are looking at. So this was just before the star party started. I set up a mission to the Orion Nebula. That is a snap. I just press that button. That's exactly how it looked in the live view. Isn't that astounding? Oh, I never get fed up of watching that. But I just wanted to say something, John, because all of these telescopes are operating live. So here we are in Chile. I'm going to snap an image of this. I'm going to open it up, maybe open that in a new tab so we can have a look at that. And then I want to go to the Canary 2 telescope, and I want to do the same thing here because this is exactly the same telescope setup actually. And we'll open this up and let's have a look. So there's the asteroid. We've got 3 bright stars at the top, 1 bright star down in the bottom right. Let's go over to the Chile image. That is totally different. I don't see any similarity, John, in the star field there at all. What on earth is going on? The asteroid, that's an image that I snapped, literally, you just saw me 30 seconds ago. And there's the asteroid. It's next to these 3 stars here. Here's the asteroid. Those 3 stars aren't even in the field of view, but it's here. What is going on? Why is the asteroid looks to be in a different position in the sky from the Chile observatory to the Canary Islands observatory?
That's a really good question. The answer to that is this phenomenon or a geometrical effect called parallax. Now, we're actually pretty familiar with the concept of parallax because we have 2 eyeballs on our heads, and that gives us kind of our depth perception. So when we look at an object with our eyes, we can close one of our eyes and it looks like our finger shifts position with respect to the background. And that's exactly what's happening here. You could think of Slooh's telescopes in the Canary Islands as 1 eyeball, and then 5,500 miles away is Slooh's other eyeball in Chile. And
our finger is representing, I guess, the asteroid.
Our finger is the asteroid. That's right. That's right. So
okay, and then the background is changing.
The background is all of these beautiful stars in the Milky Way galaxy. And so when we look, and this effect, this shifting effect is called parallax shift, the technical term for it. But the shifting effect is more dramatic the closer the asteroid is to us. So since this asteroid is just short of halfway between the distance between the Earth and the Moon, the shift of where we see this asteroid with respect to the stars is quite dramatic.
It's going to be interesting, actually. I didn't check earlier, but it'll be interesting to see whether or not there is a moment between the two when actually it does appear to pass through the same star field. But this thing about we will, I promise, I have totally derailed the structure of what we're going to talk about, John, but this is flowing well. So please go with me on this. Parallax is a really, really important concept in astronomy, isn't it? Because it gives us the ability to measure something which nothing else does, I don't think.
That's right. Yeah, it allows us to measure distances to stars.
Okay.
And what's really fascinating about that is there once was a time in human history where we thought that all of the stars were the same distance from us. And at that time, the telescope technology wasn't there to even see parallax shifts. So once the telescope was around and astronomers were starting to look at the stars, they started to notice these little parallax shifts as the Earth revolves around the sun. So we use the Earth's motion around the sun to kind of look for the closest stars to us and seeing them dance in the sky, if you will.
And a group of students last year actually used parallax. Oh, I just want to show people this in the Chile 2 telescope. So we've not only got the asteroid up here, this little streak of light, but what's this, John, down here? Because actually this is quite a good moment to talk about DZ and why we've called it DZ here. I'm just going to snap a shot here so we can show people a little bit better. Hopefully everybody can see this. It's a kind of dotted line, John. What on earth is going on there?
This is a satellite here, and its brightness of the brightness of the satellite is changing on a periodic interval.
So it's bright, then it goes dim, it goes bright, peaks again, dim, bright, dim, bright, dim, bright again, and it all fairly evenly spaced. So what's this telling us about that particular satellite?
It's telling us that the satellite is I think it's that it's rotating, isn't it?
It's spinning.
It's spinning
on its axis. So what we're seeing is the different reflections normally off the solar panels, which is the bright stuff, and that's what it's doing. And because we know the length of the exposure that was taken during this, we could also actually identify the actual satellite. We could go to a database and find out which satellite this is. But because we know the duration of the exposure, we could actually calculate its spin rate. I mean, what have we got? We got 1, 2, 3, 4, 5. We got 5 bright spots. So it's kind of 10. Yeah.
1 every 10 seconds.
Yeah. 1 revolution every 10 seconds. So, wow, that's a nice little benefit. So, John, we were talking about why that relates to asteroids, because if we could get this, and in fact, we may even notice it tonight. So this little streak that we're seeing as it falls through the field of view might change brightness. John, why would it do that?
So these asteroids, they're also spinning on their axes as they're cruising through. Again, this is why we were saying that they were dizzy. And the amount of light that these asteroids were able to reflect is a concept that's called albedo. But the asteroids are not spheres like a globe, if you will. They're almost like little clumpy potatoes or little rocks. And so as these little rocks spin, as well, I can't spin myself, but as they spin, as they're moving around, the amount of light that's able to reflect changes a little bit.
So if this bottle represents that asteroid, and there are actually quite a few asteroids that have been found which look like peanuts, because actually it's 2 asteroids which have kind of come together and merged. But if that's it, and let's say this is that is your viewpoint, so we've got quite a lot of surface area now reflecting the sunlight back to you. But as it spins, look what happens. We get a tiny amount coming, and then it comes back. Not only can we start to establish the shape of the actual asteroid by taking light curves, by measuring that brightness, but we also get its rotational spin rate as well. And that's quite important, because asteroids of a certain size, they can only spin at a certain rate before actually they would throw themselves apart. But John, I think it's time we get back to basics. We are only 25 minutes into the Star Party, and we haven't actually covered the basics. So let's take a step back. What are near-Earth asteroids? Just like 2023 DZ2 DZ that we're seeing here as the little streak.
Near-Earth asteroids are little chunks of rock that are either rocky or metallic without an atmosphere. And so you can think of them as being like leftover pebbles in the formation of the solar system. And they typically survive in orbits around the sun. These are the near-Earth objects, near-Earth asteroids. They survive for about a few million years before they either fall into the sun, ram into Earth, or are ejected from the solar system completely due to gravitational effects. And so we may wonder, well, where does the term asteroid even come from? And the famous astronomer Sir William Herschel is the one who coined that term, because at the time, when you look at some of these asteroids that are further away, like in the asteroid belt, they look a lot like stars. They're not moving as fast through the field of view as Dizzy is. And so the word asteroid is Greek for meaning star-shaped or star-like.
I didn't know that, John. So I've been doing asteroid star parties for a good number of years. We started these back in 2008 before anybody else did. And I didn't know that. And I feel absolutely ashamed because, of course, I live very close to the city of Bath in the southwest of England, which is exactly where Sir William Herschel made some of his, best discoveries with his sister Caroline. So, oh, that's a great fact. I like that. So,
oh, great.
John, what makes a near-Earth asteroid a near-Earth asteroid? What defines it? What makes it different to a main belt asteroid, which is in that asteroid belt between Mars and Jupiter?
Yeah, that's a really good question. And the near Earth asteroids are, well, near the Earth. And so then, well, how near is near, right? So 1.3 AU, if the orbit of the asteroid comes within 1.3 AU of the Earth, then that's considered a near Earth asteroid. Or excuse me, just 1.3 AU, period. So
What's an AU, John?
An AU is the average distance between the sun and the Earth. So these near Earth asteroids are the ones that are going to be kind of near where our planet is orbiting. And so we come up with a different class for them because it's important for us to keep an eye on them to make sure none of them are going to collide with our planet.
It is, exactly. And, Slooh actually entered a Space Act agreement with NASA a good number of years ago. We were asked to go there and make a presentation about citizen science because we've got a whole stack of students and members who are tracking these objects, every single night of the year, not just now, but these and comets as well. And in fact, one of the interesting things that I spotted over the last couple of weeks since Dizzy was discovered, which is, what is it, 65 days ago or something like that?
Maybe, yeah, it wasn't too long ago.
Yeah. So what happens is when an asteroid is first discovered, somebody spots basically a moving dot between two images that it takes. It's normally the surveys, these large scale surveys nowadays, rather than amateur astronomers, which is what it used to be. But they spot that and then they flag that up to the rest of the astronomical community around the world, including Slooh members, and say, hey, listen, we think we've spotted something. Please try and confirm it. So other people image around that particular area, but where do they look? They've only got a couple of images of it. So they haven't really accurately determined the object's orbit. So what happens is more and more people capture images. So Slooh members capture images of it, make astrometry measurements of its position against the background stars. And they take those measurements and then they submit those to the Minor Planet Center. The Minor Planet Center is like this clearinghouse for all of these observations from around the world. And they do lots of computation on that to determine the orbit. And actually, we've seen the orbit, the accuracy of the orbit refined day after day after day. So even changed last night between scheduling some missions last night to now. Here we can see image in Chile 2. Anybody looking? There we go. I said at 1:30, the asteroid is going to be in the center of the frame because we've been watching it come in from the right. It's going to go down to the left. Anybody wondering what this streak is? John, that's another satellite. Wow. But I think we can tell that this one isn't spinning because it's a constant line and it's obviously a lot faster. Its apparent rate of motion is a lot faster than the last one that we saw. But anyway, John, so there we are. So we've got this body of asteroids, this kind of leftover rubble from the formation of the solar system, swanning around the inner solar system, around our bit of the neighborhood, coming fairly close to Earth. Sometimes, of course, even impacting Earth. This particular one isn't. It's going to be passing between us and the moon tomorrow night. But yay world, we're going to live for another night. This one's not going to impact. But we've seen impacts of asteroids, Chelyabinsk. We'll talk about these later, maybe, John. But also some big historical ones as well. Just ask the dinosaurs. But anyway, so here we are. We've got this body, and there's all sorts of different classifications we're not going to go into now, whether or not they cross Earth's orbit, whether or not they're inside Earth's orbit, outside Earth's orbit, and come really close. One of the interesting facts on this one, John, was if this had happened, if this had been speedier and had been 19 hours ahead in its orbit, it would have actually impacted Earth, because that's in 19 hours time, or I think it's on Sunday, that's where the two orbits intersect. So they actually do kind of intersect. But anyway, how many of these asteroids are out there, and what's their distribution? I mean, presumably there are tens of thousands of little ones, but maybe fewer larger ones, and presumably the larger ones are easier to discover because they're brighter. The smaller ones aren't. Presumably the ones that come even closer to us, are even easier to discover. So how many are out there, John?
That's a really good question, because you see these things coming by, kind of makes you a little worried a little bit. And so I can report that there's about 31,500 near-Earth asteroids.
Woo.
That kind of seems like a lot. And so there's another class of asteroids called potentially harmful objects. And these are ones that come within 0.05 AU of the Earth. And
so these are the PHAs, the potentially hazardous asteroids, isn't it?
That's right, the potentially hazardous asteroids.
Which this one isn't, I believe.
Yeah, this one's going to pass by us, so we're good. We're good with this one. We've identified maybe 2,000 potentially hazardous asteroids, and so even 2,000 may seem like a big number, but if there's already 31,500 near-Earth objects, that actually only accounts for about 6% of near-Earth asteroids. But what about like the greater solar system? Well, in the entire solar system, we have 1.125 million asteroids out there.
Whoa.
And
say that number again, John.
1.25 million asteroids, compared to 31,500 asteroids that are near Earth. So there's a lot more asteroids out there than near Earth.
And you've said that they were part of the rubble from 4.5 billion years ago when our solar system was formed. Where do they come from? I mean, have they always been? Has 2023 DZ2 Dizzy always been in our neck of the neighborhood?
That's another really fantastic.
I'm full of really good questions tonight, John. Full of them.
You really are. It's almost like we planned this. But these near-Earth asteroids, they actually only last maybe about 1 million years or so. I think I mentioned that earlier, before they either are ejected or they fall into the sun. So something needs to be refueling the near-Earth asteroids that are in the inner solar system, because the solar system is like 4.5 billion years old. And so where do they come by? Where do they come from? The leading theory is that these near-Earth objects are asteroids that originally resided within the asteroid belt. And what happens is there's gravitational effects between the Jupiter and the sun that create these regions in the asteroid belt. They're called Kirkwood gaps, if you're interested in reading more about them.
I have not heard of that one before, so thank you for that. That's weekend reading sorted for me. Kirkwood gaps.
Kirkwood gaps. And so it's these regions in the asteroid belt that, if an asteroid were to wander near one of these Kirkwood gaps, the gravitational resonances between the sun and Jupiter will kick it out of its orbit and start that asteroid cruising into the inner solar system. And that's how near-Earth asteroids start heading our way.
So they're potentially the the number, potentially the population of near-Earth asteroids is actually being kind of regenerated all the time. So a bit like Doctor Who. We got a question, John. We got a question from Steve Millen, who is saying, how can normal students, teachers observe asteroids that are not listed in the Slooh 1000? Well, that is called an advanced mission. So teachers, family heads, because we've got a family membership that gives you 1+4 other licenses to use Slooh, so you can spread it around the family. But educators, them, apprentice members, astronomer members, and advanced student members can schedule coordinate missions. So I think you can see over here. So these are the missions that I've actually scheduled, and you can see over here, it's got some coordinates here. John, I think it's worthwhile me just showing, actually, if you don't mind, because I'm going to ask you about about near-Earth asteroids being part of a larger group in a second. But I think it's worthwhile just showing people just how easy it is to control Slooh's telescope. So,
oh yeah,
great question, Steve. So here we go. I'm on our normal dashboard. This is where you land when you're logged in. I'm going up here to the little dome icon. I'm going down to mission setup, and Steve was talking there about the Slooh 1000. The Slooh 1000 is our curated list of, it's actually well over 1,000 now, of some of the best and most interesting objects in the night sky. And this is how easy it is. It takes 3 steps to control a telescope, to set up a mission for one of these objects. John, pick a category, because here they are. We've got solar system, we've got planets, we've got star clusters, nebulae, galaxies of all sorts of different types, loads of stars as well. Pick your favorite. What do you want me to pick?
I always have to go with the Mission Nebulae. Those are just so beautiful.
So step 1, click your Mission Nebulae. Now, what the Slooh's recommendation engine at the moment was doing then was calculating all of the emission nebulae in the Slooh 1000, which are visible in all of the telescopes over the next 7 nights. And it's given us a list here in step 2. So here we go. All of the ones in bold are visible over the next 7 days. Any that are grayed out, there's one. Look, we've got one, the Pac-Man Nebula is grayed out. That's not visible over the next 7 days. So, I can see one of my favorites there, John. You got any favorites that you want me to pick there?
I have so many favorites. My favorite is the Gabriela Mistral Nebula.
Okay.
Always. But actually, the Trifid Nebula is also so beautiful too. Thor's Helmet is another really awesome one.
Thor's Helmet, if you are a comic fan. Anyway, look, we've selected the object. John, we've got another question coming in, which would be good for you to answer after I've shown this. It's from Pooja Gupta. Hi, Pooja. Thank you for joining us. And they're saying, how and when was DZ discovered? Because I love this story, because it's actually by one of our neighbors in the Canary Islands. But anyway, we've selected the object that we want. We press preview mission. This is saying you are going to go on a mission to Thor's Helmet at 03:45 UTC Saturday. That's actually tonight on the Chile 2 telescope. Schedule mission. I click that, and there we go. There it is. You'll get a little reminder that that mission is about to run. But if you can't be up at that particular time or watch the live telescope feeds, don't worry, because all of your images from that are automatically saved for you for the following morning. But I wanted to go back to Steve's question. How do you set up an advanced mission? So you can do by catalog and stuff like this. By the way, we forgot to mention a couple of weeks ago, we have boosted apprentice members access and features. We've now, you may have noticed, somebody messaged me tonight saying, is this a problem? Is this a fault? I can suddenly see all of the catalogs. Well, apprentice members now get access to all of the astronomical catalogs, so they can select those. But this is the one that really probably Steve was talking about. So here we go. We go into the schedule here. We select a mission slot. And this is what I did today to set up the missions for 2023 DZ2 DZ, asteroid DZ. And I came over here to coordinates. So all I did was I selected here, it's a minor planet, and I entered the coordinates that I took from JPL's website, or you can use Stellarium or the Sky, any planetarium software. You pop a name in here, which is optional, but very useful. You check its visibility, and then you can choose its image processing preset. That's just really the number of exposures that are taken, and lots of other little bits and pieces about how the real-time, Slooh's patented process, actually, the real-time processing of that image is created and then fed through to the telescope page. Apprentice members, you may have noticed that you now have access to the luminance only processing options, which we launched a couple of weeks ago, but really forgot to tell you about. But anyway, John, so Near-Earth Asteroids, here it is. Anybody who's late joining, this is our Canary 2 telescope. We've got our Chile 2 telescope looking at it as well. It's roughly in the same place in the field of view, but as we were talking about earlier, totally different star field because of parallax. So if you want to know about that, find out why that is, you can watch the recording of this star party. By the way, members can watch all of the recordings of our star parties, our member star parties, going back to the year dot. But John, we were saying that this near-Earth asteroid, a near-Earth asteroid, has a bigger category that it falls under, which is they're near-Earth objects, aren't they?
Yes, and you probably heard me multiple times say near-Earth or NEO or instead of NEA, and I have a hard time sometimes separating those two. But yeah, there is another class of object that comes near the Earth, and these are comets. They're called near-Earth comets, or NECs.
Okay, and I have to say, in the Slooh community over the years, since 2004, I have never seen more excited generated by any other type of object than comets. And frankly, you know, I wonder, can we show one, John? Can we show one? What was what was the recent comet? I'm trying to think.
ZTF. Comet ZTF was
well remembered. I blame the time of night and my aged brain for not being able to remember that. But what I've done here, I've just gone to the little magnifying glass and I've just searched for that particular object. Here we go. And what we can do here is we can take a look at all of the images that members shared of this particular comet. And it has kind of fizzled out now. So this is a near-Earth object. So this is in that same huge bucket as the near-Earth asteroids, John. Oh, this is an animation. I think we've got to open this up, haven't we? This is from Cameron. So this was this beautiful comet, C2020 E3. And let's take a quick look. Look at that. And this is when we were seeing its anti-tail, wasn't it? So it's actually, it appears, it's all a bit of an optical illusion, but it looks like there's a tail coming out at the front of it, but we've also got that stream tail coming off the back of it as well. So in the same kind of master group, John, as this asteroid that we're watching live tonight. So John,
that's right.
If you've got this information to hand, how was DZ discovered? DZ was discovered on the Canary Islands, one of the observatories on the Canary Islands, which shares our observatory in the Canary Islands as well, which is really awesome. I looked up that it was first observed late February, and when it was about 1.1 AU away from us, so pretty far away. There was a team that was involved with they used what was called the Sir Isaac, or the Isaac Newton telescope. The Isaac Newton telescope, which is actually on the neighboring island of La Palma. So the Institute of Astrophysics of the Canary Islands has two observatories, one on La Palma, which is actually home to the largest optical telescope in the world, and one on the island of Tenerife, which is where the telescopes are that we're watching live. So yeah, the Isaac Newton telescope, actually one of the oldest telescopes in La Palma. So it was discovered by a team there.
Yes, they were working on a project called the EuroNear project, which is it stands for the European Near-Earth Asteroid Research.
Okay, so one of the interesting things that I think tonight also demonstrates is actually one of the foundations of astronomical discoveries. So we were talking earlier that if Slooh members are going to be capturing a lot of images, we're going to show them next week how to turn those into an animation, a time-lapse animation, so that they can see the asteroid move against the background stars. Now, it's pretty difficult when you look at a single image. I sent out an email actually to all members about the star party, and I included an image in that, and it was from last night when the asteroid, its apparent motion was not as fast as it is tonight. So it wasn't really a streak. It was just a dot. It was just another white dot. Well, in one image, you can't see whether or not, it's an asteroid or a star. It looked absolutely no different whatsoever. So like so much astronomical discovery, and John, you can tell us about the quest that uses this in a sec. It's about taking one image. So if you wanted to discover, let's say, an asteroid, you'd have to take an image of this part of the sky tonight, and then take another image of it tomorrow night, and then compare them, compare them, or actually you do a mathematical subtraction nowadays, and see whether there's something in your new image that wasn't in this image. John, that's exactly the same process for asteroids, for comets, for nova, for supernova, and so many different discoveries in astronomy. And we've got one. Actually, now's a good time, actually, because we're going to talk about the risk that near-Earth asteroids pose to us. So now might be a good time, actually, just to tell us a little bit about Quest learning activities on Slooh, and the particular one that I know I'm referring to when I talk about this discovery.
Yeah, so on Slooh, so yes, we have this network of a large arsenal of telescopes that students and members and families can come on and use, but we also have a set of inquiry-based learning activities on Slooh. These are called quests, and quests are what Paul is showing right now on the dashboard. These are activities that step-by-step activities that walk you through and teach you how to use the telescope to learn about different things about the night sky. And in particular, we have a quest called In the Footsteps of Clyde Tombaugh, which Paul has brought up here. And in this quest, you are recreating the discovery of the dwarf planet Pluto. And what's really fascinating is you're using the same techniques that are used to discover these near-Earth asteroids and comets and nova and supernovae. So what you end up doing is you take a picture of the night sky, and then you, like what Paul said again, you take a picture of the night sky again, and you end up doing this in the quest. And towards the end, you take all of your images that you've captured with the telescope, and you put them together and you make an animation out of them. And
hopefully you can see in the center of this animation, which is the one that I did when this quest, just where my cursor is here, you can see the little dot moving across the night sky. And that's exactly what Clyde Tombaugh saw back then when he discovered Pluto.
And when Clyde Tombaugh was doing this was with photographic plates, and these plates were massive plates.
Yeah, 20 inches or something in square. Yeah.
So what's really cool about that animation is that's what Dizzy would look like earlier. When it was like further away, it would just look like Pluto did, just moving, little dot moving with respect. And you can really see how,
so the images I took last night were at, I think, half-an-hour intervals, and it barely moved across the field of view, because it was further away. So its rate of motion looked a lot slower. So tomorrow night, if any Slooh members want a good challenge, try and capture it tomorrow night, because when it's making its closest approach to Earth, I think it's slightly closer, isn't it, John, than half the distance between the Earth and the Moon.
That's right.
Can you give us some figures on that? Just how close is that?
It's about 45% of the way from Earth to the Moon is where it's going to be.
Okay, and I think didn't we have some figures somewhere for that? I
thought. Oh yes, the closest distance that it's going to be is about 108 miles, which
Okay.
is about 175,000 kilometers.
That is pretty darn close, pretty darn close. So anyway, look, we've still got the live view, so please, Slooh members, carry on snapping images. When it gets to the top of the hour in 10 minutes time, I change how Chile 1 telescope and the Canary 2 telescope are going to capture the image. They're going to suddenly recenter the Near-Earth Asteroid, and also they're going to be color missions. And what we're going to see there, I'm hoping, John, I'm hoping we're going to see a white line followed by a red, green, and blue shorter line, about half the length of the white line. And we can explain that when it comes to it. But I think there's another question here, isn't there, John, before we talk about the risks. So Steve's there as well. Steve is saying, I'm impressed with the great material in Slooh's quests, particularly Mystery of the Island Universe as well. Thank you, Steve.
Oh.
We will pass that on. Who wrote that one, John? Who wrote that quest?
That was a Cameron quest, and
Okay.
it was revamped to be a part of our high school astronomy learning progression.
Cool. So oh look, we're still capturing some great images. Oh, I'm so pleased. You know, you wouldn't believe how nerve-wracking it is before one of these, John, because I was scheduling all of these missions today and getting the coordinates and checking them on JPL and checking them elsewhere. But even between last night and this morning, those coordinates had changed by about a quarter of this field of view. So if I had scheduled these actually on Tuesday, when we decided to do the star party, we would not be seeing DZ right now, because that orbit determination by the Minor Planet Center, because of submissions by amateur astronomers and students around the world using Slooh's telescopes as well, because they've been making submissions for this, have helped to determine DZ's orbit more accurately. And therefore, we understand far better the risk that this particular near-Earth asteroid poses to Earth. Now, way back when this was discovered, there was a chance in a few years' time that DZ could impact Earth. And that was because the error values in its orbit, we weren't certain of its orbit. So there was a risk there. But that has been chopped down day after day as each measurement is made using Slooh's telescopes and other telescopes. It gets more and more accurate. And therefore, we now know that it is extremely unlikely that DZ will impact Earth over the next 100 or more years. All right, so we're safe for tonight anyway, aren't we, John?
We are. That's really cool that the members are able to use Slooh's telescopes to see these objects and submit them to the Minor Planet Center.
Yeah,
it's like they're doing real science with.
And I was talking to the Dune School today in India, and they're very keen on undertaking and participating in some of our new independent study programs, which are designed for students, but other members will be able to do these as well. And a lot of that's going to be monitoring variable stars, like Michelle Park, who was what was she? She was a 9th grade student who joined Slooh of her own volition. Nobody really, it didn't come to our attention until she publishes a scientific paper, because she spent 2 years using Slooh's telescopes to study a particular type of variable star. Michelle Park is a star in her own right, and she's actually just got into Stanford. So, I mean, that's brilliant. So we are extending all of these independent study opportunities for students using Slooh. But John, so we talked about there, the risk of DZ impacting Earth, but do they ever impact Earth, asteroids?
They do. It happens often. Luckily, it doesn't happen too frequently. But in a way, if you've ever seen a shooting star, that's actually a very small chunk of an asteroid that's cruising into the atmosphere. So some of the smaller rocks, some of the smaller asteroids we can't really see until they come in, but the bigger ones we can. And there have been some events that have happened in the past of asteroids colliding down. I think one of the most most famous one is probably the asteroid that took out the dinosaurs.
That's Chelyabinsk. That's in is it the Bay of Mexico, around there?
This one, it's
Oh no, what was the name of it? Oh,
it's a Chicxulub.
okay.
It's named after a
Yes.
community that's right by where the crater impact was. And I think when I was young first and heard about the dinosaurs being taken out with an asteroid, for some reason I thought that the Gulf of Mexico was the crater. But it's actually not. It's there's the Yucatan Peninsula, and the crater is right at the tip of the Yucatan Peninsula.
Okay.
This asteroid impacted Earth 65 million years ago, but it was quite large. It was about 6 to 9 miles in diameter, whereas this one, the measurements, the diameter of Dizzy keeps changing as more and more data gets submitted to the Minor Planet Center. So it was way bigger than Dizzy was.
So interestingly there, and John, we've got a 6 to 9 mile diameter. That's 10 to 15 kilometers for people in Europe and a lot of other places.
Apologies.
Peculiarly, here in the UK, we've gone metric, but we still use miles as our distance measurement for some reason. But so there's this huge asteroid that can get through our atmosphere. It's big enough to survive and actually impact Earth. You talked about meteors, which is just a meteoroid, which can be as small as a grain of sand. It can be a pebble. That never reaches the ground, or rarely, because they burn up in the atmosphere. And there was that superb example in Russia a few years ago, wasn't there? The Chelyabinsk. And there was a historical one in roughly the same region in Russia again, called Tunguska. And
that's right.
Those asteroids didn't actually get to the ground, did they?
No, they didn't. And so those asteroids, they were traveling really fast. They were traveling maybe 2 to 3 times faster than what Dizzy is right now.
Wow.
And so when those asteroids came in and crashed into the atmosphere, which we know is gas that's surrounding the surface, the atmosphere kind of acted like a wall for the asteroid. There's this effect called ram pressure, where the asteroid crashes into the atmosphere. The atmosphere doesn't really react that much. It just heats up, and that heats up the asteroid itself, and the asteroid itself just basically explodes in the sky.
Wow.
And what's really cool about the Chelyabinsk event is that happened in Russia, where a lot of the folks over in Russia, they have dash cams, and this object was able to be seen crashing into the atmosphere throughout many dash cams. And those dash cam videos were able to be used in conjunction with other telescope images to help constrain or figure out what the orbit of that object was before it crashed into Earth.
Wow. One of the big problems with that, of course, was because it was burning up in the sky like that, lots of people saw it and went to their windows to look at it. And the airburst then the shock wave that came off that, most of the injuries were glass injuries, people standing in their windows and their windows breaking when the blast hit them. But John, we have got other examples that I don't think we'll talk about now, but what can we do if, we've seen movies, Armageddon, Deep Impact, what could we do today if we discovered an asteroid, a large asteroid? Because don't forget, this is quite a rare event, actually, because this asteroid is somewhere between 35 meters and 88 meters in diameter. That's about 115 feet to 350, no, maybe not quite that much, nearly 300 feet in diameter. It's for an asteroid that large to be discovered this late and then to pass so close to Earth is very rare. NASA estimated that combination of factors will only occur about once in a decade, and we have covered a couple. actually over Slooh's time. But what could we do, John, if we discovered an asteroid which we determined is on a collision course? Do we get on the phone to Bruce?
No, we don't. We definitely don't want to do what happened on the movie Armageddon. You don't want to go and blow it up with the big nuke, because all that's going to do is turn one big asteroid into a bunch of littler asteroids that are just going to come and hit us like a shotgun. So what we want to do, and what's really awesome, is within the past year or so, NASA tried to test what can we do. They launched a probe called the DART probe, which was the Double Asteroid Redirection Test, towards an asteroid that was named Didymos. And what's cool about some of these asteroids that are way out in the solar system is, gravity is always working. Gravity is pulling things together, pulling all matter together. And so there are some asteroids that have little smaller asteroids orbiting around them, like we have the moon orbiting around the Earth. And so what NASA did is they wanted to take their DART probe, and actually slam it into this little moon orbiting around Didymos. The idea is maybe we can alter the orbit of some of these asteroids, maybe by slamming something in them. That's how you would do it. You want to change the energy of these objects. And when that occurred, there was a myriad of Slooh members who were doing coordinate missions and taking a look at the collision. And you could actually see the debris field from the DART mission crashing into this asteroid moon. And you can still see them today in Slooh's telescopes. They're part of the Slooh 1000.
Sorry, don't carry on.
This debris tail. This is a fact that comes from one of our quest authors, Cameron McEwing, who wrote the Mystery of the Island Universes. He measured how long that debris tail was. It's longer than any structure that's any human-made structure on the Earth.
Wow.
So in a way, that is the longest human-made object in the solar system.
I like it. Hey, John, well, look, we're just looking at one of the last missions in the Canary 1/2 meter telescope. Here we go. These two lines here are the Near-Earth Asteroid 2023 DZ2, Dizzy, nicknamed Dizzy, whizzing through the sky. But up here we've got another line as well, John, and this is another repeating line: bright dark, bright dark, bright dark. It's another satellite, and it's a spinning satellite, as we can see whizzing through here. So
it's like it's going in formation or something.
It is
getting into formation.
John, we're running out of time now. What else would you like to talk about to viewers? We are going to see the asteroid appear in a different way now in the last 15 minutes, where we're going to see it come back into the center of the image. And I think I did color missions as well. So, but what would you like to talk about, John, in this last little segment?
Well, I would like to, a couple things. We're always building more and more quests. I know that a lot of folks here are just now learning about quests, but we're
just learning about Slooh as well.
Just learning about Slooh as well. That's right. But we're starting to write quests that start teaching you how to do activities like what we're doing right now. Look at different asteroids and different comets, and learn how to go on these coordinate missions and capture these objects. In fact, we're writing a quest right now about the biggest asteroid in the solar system called Ceres. And Ceres is going to go right across one of the most famous galaxies, M100, in a couple of days. So If you can get yourself onto Slooh's telescopes in a couple of days, look out for those missions. I've scheduled a few of them.
Oh, cool. Okay. Listen, we have neglected Canary 3, the Canary 3 Deep Sky Telescope. Right at the beginning of the star party, I was telling everybody this is one with a huge field of view. You can see a huge expanse of the sky. This is great for capturing the Andromeda Galaxy, but also huge nebulae as well, like the Rosette and the Lagoon Nebula. But this is going to be the series of images that we're going to use next week. And I'll show members how to create a time-lapse animation. Don't know if you can see it, but there's the asteroid down here. When we started off, actually, the last time we looked at the Canary 3 telescope, it was way up here. So what we're going to do next week, if you've captured all of the images, just snap them like I have there. We're going to turn that into a time-lapse animation that shows Dizzy speeding its way across the sky, whizzing through here. We may even have captured some of the other satellites as well. But let's take a quick look. John, what else did you want to cover?
And another thing I thought was kind of interesting, especially because didn't you say that the diameter of Dizzy is now estimated to be around 150?
Yeah,
feet?
so 115 to something nearly 300 feet. So there's this huge range. And if you saw the initial media reports of this about a week ago, they had far, far greater estimates of its size. So it was a lot bigger, they thought. But that has come down and down and down. But it's not going to be until tomorrow night where we can truly understand how big Dizzy is and also what shape it is. But John, this goes back to something that we talked about right at the very beginning, didn't it? How do we make those size assessments of an asteroid like Dizzy, and why has it changed, John? It has to do, doesn't it, with how bright it looks, but also there are some big assumptions that astronomers are making in that little equation as well, aren't there?
There is a quantity called the albedo that astronomers have to assume based on some other effects. And what albedo is it's the ratio of the reflected light to incident light. And I think one of the best ways to understand or see albedo is to look at the moon. So over here we have a dark albedo on the Maria. So there's not much light reflecting versus the highlands of the moon where we have more light reflecting, and so they look brighter. There's different kinds of asteroids depending on what they're made out of, and depending on what they're made out of, they assign a certain albedo value to their models. And so typically when you do model fitting, you want to start with keeping some of the model values constant. And as you get more and more data, you kind of have more flexibility to let some of those values float around a little bit. And so this is why it's so important to get as many measurements of these objects as possible, because the more data we have, the more information and sophisticated information scientists can get from the data, such as how big these are. And it also will help constrain them, make their error bars a bit smaller.
Yeah. And that's exactly what we were saying earlier as well. Some people's observations and measurements of its brightness may have been, if it is, an odd-shaped asteroid, which many of them are. Some people may have captured it when it was like that and actually looking quite dim. Other people may have captured it like that. So the more data we have, we start kind of averaging out all of that and also understanding its spin rate and stuff like that. But John, I said that tomorrow night really is going to be the night when we really truly understand the size of this. Why are these near-Earth asteroids that come particularly this close to Earth so important for us? And are there other ways that we can, capture images of these objects other than in optical telescopes like Sloohs?
Yeah, yes, definitely. One method is by using radar, using radio to map these objects. In fact, this is one, they use radar to map the surface of Mercury actually from Earth and measure the orbital speeds of Venus as well. So typically, though, these asteroids don't get close enough to us to use radar technology, but sometimes, like this one, when it gets right literally in our doorstep, not right next door, we can use radar to get more information. And as you see, as the rate, if you think of these asteroids as the P, and the bottle that we were using earlier as our example, all of those little crevices in the asteroid are just going to cause reflections of the radar waves. And based on those reflections, we're going to be able to learn a lot of information about these objects.
Yeah, I mean, we were talking the other day when we were preparing for this particular star party, but we did a star party a good number of years ago with NASA, and we talking to some guys using one of the radio telescopes at NASA or JPL, I've forgotten where it was. But it was the Halloween comet, which we dubbed Spooky. And we had no idea what shape or really what size that particular asteroid was. And we were watching live views very similar to this with a streak in the sky. That's the asteroid. And as we're interviewing the astronomer, the radio astronomer, he suddenly said, "I've got to show you something, Paul. Can you see this on my phone?" And he held his phone up, and it was the first radar image from the radio telescope that they had captured of this asteroid that we had dubbed Spooky. We dubbed it Spooky because it was making its close approach on Halloween, the night of Halloween, when he showed us. So look this up, folks. Look up the asteroid Spooky. When he showed us the radar image, he was showing us an image of a skull with two dark eyes in it, exactly the shape of a skull. And it was just one of the best live star party moments we've ever had. But it is going to be interesting to see whether or not they can capture good quality radio observations of this from the radio telescope, so that we can know exactly what shape and size it is. And what that then enables us to do, John, when we've got a true measurement, when we know how big it really is, we can test those assumptions of the brightness, that albedo that you were talking about. We can say, well, hold on a sec, we thought it was going to be 115 feet in diameter, but actually it's bigger than that. So therefore our assumption was that it was darker than it was, which helps us then use better factors in the future when we're assessing the size of these. But that's really good. Oh, we've got a question for you, John. This is a difficult question, I think, to answer, because I certainly don't know the relative speed of the moon, relative velocity of the moon. But Pooja Gupta is asking, is DZ moving across the sky faster than the moon? And a couple of ways of answering that, I guess. True speed and then relative speed.
That's true.
And it's always good to say, scientists are always happy to say, actually, we don't know that, but we'll find out.
Yes, that is something I'm not familiar with on the top of my head.
So that there are these important, there's this important thing, isn't there, in astronomy, and we hear it quite a lot. The use of the word apparent. We hear it a lot when we're talking about the brightness of object. We're talking about the apparent brightness of something rather than its absolute magnitude, its actual brightness. And we also have relative velocity and things like this, or apparent motion. So what we're seeing at the moment is the apparent motion of DZ going through the sky, but that doesn't actually represent its speed, because its velocity, that's 17,000 miles per hour that it's actually traveling through space, has been constant from last night to tonight. But last night it only appeared as a dot because its apparent rate of motion, because it was further away, was a lot slower than it is tonight. And then tomorrow night we're going to see that line, which represents the distance, the apparent distance that DZ has moved over 50 seconds, probably increased by a factor of 3 or 4, my guess would be. So John, have you got any better answer?
Oh, absolutely. Yeah. So one way to think about the actual true velocities of these objects is thinking about, well, how's gravity working here? So the moon is bound to the Earth by gravity, and it's doing that because it's actually not moving very fast. It's only moving maybe about a kilometer a second, versus how fast Dizzy was moving. So Dizzy is moving so fast near us that it's not going to be bound to the Earth. It's just going to kind of pass right by. So Dizzy is moving much faster than the moon is.
Listen, folks, we are nearing the end. Has anybody got questions? Don't forget that when you are, no problem, Pooja. Thank you very much. It wasn't a definitive answer, but I think it depends how you're looking at it, literally. But don't forget that if you're a Slooh member, you can actually join the actual webinar rather than just watch on YouTube, and you can interact with us. You can ask questions and stuff like that, as well as be snapping your own images of the asteroid or whatever else we're looking at. But has anybody got any questions before we wind up this particular star party? Don't forget, members are going to be observing Dizzy tomorrow night as well. It'll be a little bit more difficult to capture because it's going to be very low. So it's going to be, I think it gets high enough a lot later at night, about 02. Where will Dizzy go next, John? Bruce Williamson is asking. Well, I think the answer is around and around and around and around. It's got an orbital period of, is it just over 3 years, Dizzy?
Just over 3 years, that's right. Yep.
Okay, and it's orbiting the sun, but it is intersecting Earth's orbit, which is why it's a near-Earth asteroid. That's right?
That's right. And that particular configuration is called an Apollo orbit. So they actually classify near-Earth asteroids in 4 different classes based on their orbits. So if you're interested in learning more about that, definitely check it out.
And I think I'm right in saying I think it's forward rather than back, but in 19 hours time, probably that's from tomorrow night, I think. So I think this is on Sunday. It's actually going to cross Earth's orbit. All right. So I think that's really cool. It just shows you kind of, it can happen, and it does happen. We saw it in 2008. Right, this was when Slooh members got switched on to the threat from near-Earth asteroids, and that's when this group of members got together to start studying them, to try and track them, because there were huge telescopes around the world discovering these things, but then they get lost because nobody was making these follow-up observations. But in 2008, Slooh members were among, I think, just a handful of people around the world who managed to capture 2008 TC3. That particular asteroid was the first asteroid that was discovered before it impacted Earth. And it impacted Earth over Sudan, over the deserts in, I think it was Sudan. And Slooh members managed to capture images of that just a couple of hours before it impacted Earth. We saw another one. We did an asteroid show a few years ago, and the very first asteroid that had been discovered this year impacted Earth. It happened, I think, on January the 1st or January the 2nd. So whatever year it was called AA. That was its designation because it was the first one of the year. And we didn't actually know about that until it had impacted Earth, because lots of different defense listening devices heard it impact over the Atlantic Ocean. John, we've got some more questions coming in. Bruce is asking, in front of Earth or behind us? I think it was in front. I couldn't be totally sure about that, Bruce. I would need to look at the orbital diagram, which you can find actually on NASA's website, so you can see, and you can normally animate those diagrams so that you can see where it is. But there was a couple of people who did this calculation where they artificially delayed or advanced Dizzy's orbit, and it then landed up intersecting Earth's orbit when Earth was right in that spot as well. So more questions, John. One from Lauren here. Will Dizzy ever break free from the gravitational pull, or is it forever destined to orbit? Good question.
That's a good question. It more likely than not, it's definitely going to keep on its track orbiting around the sun. As I mentioned earlier, these near-Earth objects, they only do that for about 1 million years or so before their orbits decay and they either fall into the sun or they get too close to one of the planets and gravity slingshots them out of the solar system. So those are the two in scenarios for a near-Earth object. Well, I guess there is the third in scenario of like crashing into the Earth itself, but that's one of those three is going to be the end of the story for every near-Earth object.
Okay,
good question.
And of course, 4.5 billion years time, we've got the sun expanding as well, which will presumably suck up a load of them as well.
Yes,
Yari
and us.
Exactly, nearly. Yeah, we definitely need to get on our spaceships before that happens. Yari Bachman, long-time member, is saying he's looked up on Stellarium and there was a 50-second, I think it's second, I can see there. And when we're saying second, we're talking about the actual distance in the sky. Difference between the Canary observations that we've seen, the apparent position of it against background stars, to the Chile ones. So Yari's asking, could we get images to fit to each other? Could be close. I think from the beginning in the end, I think there's going to be a way of doing that. So that'll be an interesting one. If people haven't snapped everything, 50 minutes, it was 50 minutes, right? Okay. Yeah, well, the field of view, both those telescopes, Yari, is about, I think it's 30 or 36 minutes, arc minutes. That's a nice image. This is Milton's mission that we've now gone on to. Now, I don't know what Milton has scheduled this for. He's got some coordinates here, but there's a beautiful looking, looks like a barred spiral galaxy to me, John, that one. Absolutely. So our Dizzy missions have finished. Let's just check, make sure we haven't got any last ones here. Yeah, so we've got Flame Nebula coming up next on this one, on Chile 2. So we've got normal members missions. So I was looking down here, by the way. So these are all of the member missions. Got a galaxy cluster scheduled by Chris. Beauty Dollar has got a globular star cluster coming up, a Bennett object from Cole. Oh, NGC 104. Isn't that the tarantula?
I think so.
Yeah, I think it may be. Astro UA Wildcat. There's some good names coming in with all these students. Oh, and somebody is actually trying to schedule that comet that we looked at earlier, ZTF. Joe Peartree. Be interesting to see how that comes out. It looks like it's passing a galaxy or nebula there. Loads more in here anyway. Crystal, God, goodness me, there's loads of really cool missions, and I can go in here and I can say join that mission. That's a nice little feature, isn't it, John?
This is great.
So lenticular galaxy. I'm not staying up until 0240 because I've got to be up in about 6 hours time, but I would love some images of that particular lenticular galaxy, Messier 86. So what I can do is I can say join this mission, and I have just joined that particular mission, which means that all of the images from that mission, from Black Belt Ash, is going to be stored and available for me on my dashboard in the morning. So this is where they appear. Now this, John, is going to be stuffed full of Dizzy images, isn't it? If I go down to my photo roll down here, look at all these images that I've got from all of my missions tonight. Hopefully Slooh members have got those as well. I did just want to take a quick whiz down here to observations just before we go, because we've been looking at little bright white spots all evening, looking at Dizzy, but look at some of the other stuff that members capture. This is the Dumbbell Nebula. I think one of my favorite planetary nebula, John. I think that's a great one to use in the nifty Nebula quest, and probably a couple of the other quests. Life and Death of Stars quest is a great one to capture that in. Butterfly Nebula here. What do you got? Oh,
Oh,
So this is not an image that was snapped a lot from the live telescope views. What this member LV has done is capture lots of data, all the scientific data that also a lot of members receive, called FITS data, so that they can process their own images, and that's what they have done there. So that's pretty cool. I wonder if there are any solar. Oh, a little comet there. What's that little comet? Oh, that is what ZTF looks like now. So that's fascinating. So that was March 2nd. So, okay, a few weeks ago, but we saw that glorious image of comet C 2022 E3 ZTF earlier.
was this the one with the anti-tail?
Exactly. So that glorious looking one earlier, but this is how it diminished as it moved further away from the sun. So that's pretty cool. Eagle Nebula, always a favorite of mine. Oh, we have seen some astonishing solar activity over the recent couple of weeks, really. I wonder if there are any in here from today. Oh, this is one from today. Ernest has shared that. Look at all this solar activity. Oh, look.
Oh, whoa.
Kui Chang has put together 2 images here to splice them together to show the sun today. So it's not just the nighttime telescopes we've got here at Slooh that you can enjoy. We've got the daytime telescopes as well, which is the Slooh Solar Telescope at the Canary Islands Observatory. It's online for most of the day, and you can watch live video through a very special camera that looks at the sun in a special wavelength. So don't ever try and look at the sun through a telescope yourself, but we can see sunspots, we can see filaments, we can see active regions, we can see prominences here, and frankly the level of activity has been absolutely astonishing over the last couple of weeks. Exploding galaxies. So this is a galaxy. So I'm talking to another school at the moment. They want to embark on an independent study program to search for nova and supernova. We did a show a good number of years ago with a group of students who actually discovered a supernova in this very galaxy. It's called the Exploding Galaxy. And there was a supernova. What's a supernova, John?
Supernova is when a really big star ends its life and it erupts in a massive explosion, generates a bright explosion that outshines the entire galaxy that they reside in, which is how these students are going to be able to see these supernovae in other galaxies.
Exactly. This is a comet that's coming up, which is exciting a lot of our members at the moment. This is forecast to be quite a good one, so let's keep an eye on that. Wasn't discovered that long ago. It's discovered this year. Oh dear, why are all comet names, why do they all seem to be so difficult to pronounce, John? We'll have to look this one up, won't we? So, but anyway, listen, I thought we would just share a few community highlights there from students and other members. So I think it's about time we should wind up, but I would like to introduce somebody who's been working behind the scenes in the Zoom event called Slooh Events. But it's Gretchen. Gretchen has started work part-time for us at the moment as our Slooh events manager and coordinator, and also a customer success manager. What have we got coming up at Slooh, Gretchen? We got a number of other star parties, haven't we? Because we do these every week.
We do have a bunch coming up, and it's a super great way for members to get together and learn and then get their questions answered. We've got the Tuesday star party that's every week, and we talk about what's happening with the sun. And these are the Tuesday at 8 and the Sunday space chat are all member run star parties, which is like super fantastic. Tuesdays we learn about the sun from members, and that's hosted by Keith and myself. Keith always shares just a fantastic presentation about what's going on in the night sky, how we can look at it in our backyard, how we can schedule missions on Slooh. And it sometimes goes on for quite a while. We have the infamous after party now, which also talks about other interests that us as astronomers have, like music, and how does that tie in to astronomy. So it's super cool. And it was so cool that we decided to add Sunday space chat every first and third Sundays, where it's just casual end of the weekend. Hey, you guys, what were you looking at? Did you have any cool missions? What's the topic du jour? Let's all share just in casual little format. Universe Explorers of Maine is fantastic. I love that one because it's like that virtual planetarium. Like when you were a kid, when you go to the planetarium, you lay back and watch the show. That's just what it's like. And I love it. It's super fun. And then of course, the upcoming hybrid total solar eclipse star party. Super exciting.
It's gonna be a good one.
Yeah, so it's fun.
So is that date right?
Actually, you know what? That is like the old graphic, darn it all. You're right. So you guys check it out on the page.
Yeah, on the Star Party page. So actually I will share, I will just share that and show people where that is.
Yeah, actually I've got it like right here. I can
so but all of our Star Parties and all of our professional development webinars for teachers and our special student Star Parties are all available here. I just went to the little hamburger menu, the 3 lines, and went down to Star Parties. So here are all of the Star Parties, so you can watch this tomorrow. Maybe you already are watching this tomorrow.
It's true. Maybe
maybe that's true. But anyway, we got some other great webinars here. We got the Sunday space chat there. We got professional development webinars here. But you can go through all of these and you see some of our past eclipse shows. But you can also just flick through here and you can see the upcoming Star Parties as well. And we've got here's the Ningaloo total eclipse. It is 20th 0100, so that is right. No, it's not. It is the 19th. So we have got a discrepancy there that we'll sort out. That's right. So the actual event is on April 19th, the day of April 19th. So anyway, that's going to be a good one. It's going to be a really difficult one to cover. 25 days time is the countdown for that. They are always incredibly exciting events. But anyway, thank you very much, Gretchen, for that, and welcome to Slooh. John, thank you so much for all of your insights tonight. My favorite nugget of the evening is definitely the naming of asteroid by Sir William Herschel.
Thank you so much.
So that was really cool. And I hope if you're new to Slooh, you've enjoyed this. Come along, join this community. It's an absolute ball. A lovely group of people. One of the best place actually I've ever been on the internet. And we've been around here for 20 years, but also students and educators. If you want your students to be learning astronomy in an engaging way, such an engaging way, with curriculum aligned learning materials, our quests, but using the live telescopes, all of the quests that John's team develop, all have use of those live telescopes. So your students capture their own data to learn about astronomy. But that is it for tonight. 1:30 here in the UK. John, it's what, 6:30 now for you in the evening?
That's right.
Presumably dinner is beckoning.
Dinner is beckoning, but still have the sun a little bit over here in the sky.
Okay. So I shall see that. We got one last question from Olga Connolly. Hi, Olga. No question. Oh, no question. After returning to CA, this was great listening as ever. Well, thank you very much, Olga. That is a superb way to end the Star Party. So I hope everybody else has enjoyed it. If you enjoy this kind of stuff, come over, join Slooh. You can do it as a student, an educator, a school, a district, or an individual member. You can have a family membership as well. So that's absolutely great. We will sign off now. Thank you very much for joining us this evening to watch the Near-Earth Asteroid 2023 DZ2, nicknamed Dizzy, whiz towards Earth tonight. Don't forget, it's going to be making its closest approach tomorrow night. We're all safe, but Slooh members are going to be watching in the live telescopes tomorrow as well. So good night, everybody.